Today we're going to talk about Hess's law and a little bit of intro into some other thermochemistry as well. So Hess's law. Hess's law says that in going from a particular set of reactants to a particular set of products, the change in enthalpy, the overall net change in energy, is the same whether the reaction takes place in one step or a series of steps. So in this graph you can see that if you take a straight path, the change in energy is the same. If you take a more wild, multi-step process, you will end up with the same as well. So delta H of a reaction is equal to the sum of the heats of formation of the products minus the sum of heats of formation of the reactants. So, for example, you can calculate delta H for the combustion of methane, CH4, and what you do is you look up the heats of formation for each of these compounds, and what you end up doing is you take those reactions and you have to make sure that CH4 appears on the reactant side. So we're going to reverse reaction number one. So you'll be given a series of reactions. What you have to do is you have to take these reactions and manipulate them until you get something you can add up and it equals the equation they're asking you about. So equation one, because we need CH4 on the left-hand side, we're going to reverse that. And what that does is it changes the sign of delta H from negative to positive. So to keep reaction number two unchanged, because CO2 and only one CO2 needs to be on the product side, so we'll just leave that one how it is. So C plus O2 becomes CO2, and that's negative 393.5 kilojoules. So we multiply reaction number three by 2 because we need two H2Os on the right-hand side. So we get 2H2 plus O2 becomes 2H2O, and we also have to multiply the delta H to get the same value. Remember, we're trying to look for the delta H of that top equation. We can now add these together, and if something appears on both sides of the equation, we can cancel it out. So we cancel out the carbon, we cancel out the two H2s, and we get CH4 plus 2O2 becomes CO2 plus 2H2O, which is the reaction they asked us about. And that gives us, when we add up those delta H's, it gives us negative 890.36 kilojoules for our final delta H. Calculate the delta H for the combustion of methane. The other way to do that is to just look up the heats of formation for each of these, CH4, O2, CO2, and H2O. If it is in its pure form in nature, in its an allotropic, lowest energy allotropic form, it's 0 kilojoules. And so you can add and subtract these. So products minus reactants, we get negative 393.5 plus 2 times negative 285.83 minus negative 74.80 kilojoules, and we get the same answer. So it doesn't matter how we calculate this, as long as we're using good data. So the units of measurement for heat are the joule, which we learned before, and the calorie. So specific heat is this idea. It's the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So the calculations that we tend to use with specific heat are Q equals mc delta T, or you can solve for specific heat, and C sub P is specific heat, which equals Q over m delta T. So C sub P is specific heat, Q is the heat lost or gained, and delta T is the change in temperature, and m is mass. So solve the heat equation for change in temperature. You should get that delta T is equal to Q over mCp. So there's a list of specific heats for a lot of different substances: water, ethanol, solid water, vapor water, aluminum, carbon, iron, copper, mercury, lead, and gold. It's the amount of heat required to raise the temperature of 1 gram of substance by 1 Celsius degree. You'll notice that water is the highest in this list. So there's also latent heat of phase change. So there's the molar heat of fusion, which is the energy that must be absorbed in order to convert 1 mole of solid to liquid at its melting point. So this isn't about just changing the temperature, this is about the energy that has to be absorbed to go from solid to liquid, to melt something. There's the molar heat of solidification, which is the energy that must be removed in order to convert 1 mole of liquid to solid at its freezing point. There's also molar heat of vaporization, which is the energy that must be absorbed in order to convert 1 mole of liquid to gas at its boiling point, and molar heat of condensation, which is the energy that must be removed in order to convert 1 mole of gas to liquid at its condensation point. So here's a latent heat problem. The molar heat of fusion of water is 6.009 kilojoules per mole. How much energy is needed to convert 60 grams of ice at 0 degrees Celsius to liquid water at 0 degrees Celsius? So you take the 60 grams, you multiply it, divide it by the molar mass of water to convert that from gas to moles, because it's a molar heat of fusion. Then you multiply times the molar heat of fusion, and it gives you the total number of kilojoules. So you take the mass of the ice, the molar mass of the ice, and then the heat of fusion. So the heat of solution is the amount of heat energy absorbed, endothermic, or released, which is an exothermic, when a specific amount of solute dissolves in a solvent. So, for example, things like sodium hydroxide has a heat of solution that is negative, which means it is exothermic. It produces heat. Ammonium nitrate, NH4NO3, absorbs heat. It draws heat into itself. Potassium nitrate draws heat into itself. And hydrochloric acid, when it dissolves in water, HCl, produces heat as well.